Welcome back to Calculus 2. In this video we're going to talk about doing some applications of calculus in polar coordinates. We're going to specifically start off with finding area. So how does finding area correspond in polar coordinates? Well, since we're iterating along our theta, we're looking at, say, we're integrating from some theta value to some theta value, alpha to beta. So like from this alpha to this beta of, let's say we have, I don't know, this thing. Well, what we'd be finding would be the area of this fan-shaped region. So the idea behind how we do it is, instead of using just an area of a rectangle, we use the area of a sector of a circle. The area of a sector of a circle is 1/2 r squared times the amount of angle that's cut off. So if you're looking at one of these sectors where you have an angle length that is, you divide it up into smaller pieces. If you look at one of those pieces, so we'll just take this one, we broke up its angle into delta theta, and then if delta theta is small enough, these two r's are fairly similar, but you just pick an r to be it. It could be one of the end points. It could be, just the average of the two. But regardless, you let some r sub k be your radius for that sector, and then your area at that a sub k is going to be 1/2 times r sub k squared times delta theta sub k. Then you sum them all up. A sub k, k equal 1 up to n, is going to be sum k equal 1 up to n of r sub k squared theta sub k. And just like before, you turn this into a Riemann sum with limit as n goes to infinity. Basically, as the partition of your angle goes to 0, you get an integral. The integral from alpha to beta of our 1/2 r squared d theta. It's r of theta, but r squared d theta. So that's where we get our formula. Alpha to beta 1/2 r squared d theta. And we might use this area differential for some other things later, because this is basically how you calculate area with a Riemann sum. So let's go ahead and do this. Let's look at an example. We want to find the area inside one loop of the lemniscate. R squared equal 4 sine 2 theta. So we are going to integrate. Well, we need to figure out what our bounds would be. Probably the easiest way to do that is just to graph it real quick. So we look at r equal 2. It's literally what we plugged in last time, isn't it? Yeah, I think I actually even the corresponding problem from the last section. So if you look at that, we just want one loop. I think that'll go from, let's see, 0, trace, 0, that's fine, to pi over 2. Yep, that'll work. So just from there, 0 to pi over 2 of 1/2 r squared d theta, and in this case r squared is 4 sine 2 theta, so 0 to pi over 2 of 1/2 times 4 sine 2 theta d theta. Bring out the 2, 0 to pi over 2. Integrate sine, you get negative cosine. And since I had 2 theta inside, I'm going to have an extra 1/2. So negative cosine 2 theta, evaluated from 0 to pi over 2. So that will be negative cosine of pi plus cosine of 0. Cosine of pi is negative 1, so that's positive 1 plus 1 equal 2. Alright, we're going to do this problem. This is exercise 11. Find the area shared by the circle r equal 2 and the cardioid r equals 2 times 1 minus cosine theta. Alright, if you look at the rough graph of this in the calculator, of course the circle is like this. That's a circle. That's a circle. It is then, the cardioid is like this. Like so. So the area shared by them is in here. Now, if we were trying to find like this area over here, we'd have to do subtractions because we'd have to do this minus this. Just like if you're doing rectangular integrals. But it's more of a sum of an area because integrating, say, this one from 0 to pi over 2 would get us this. Integrating this half of the circle would get us that area. So, really, what we want is one of these. We can just, since it's symmetric, we can just double it. One of these, which would be 0 to pi over 2 of, let's see, area is integral 1/2 r squared theta. So 2 times 1 minus cosine theta times 1/2 squared d theta. And then we want to add, times 2. And then we'd want to add half area of the circle. So that's easy enough. I mean, 1/2 area of the circle, it says radius 2. So 1/2 pi times 2 squared. And then plus 2 times, let's see, square the 2, then half it, you're back to 2. So can bring out a 2. Get 4. Integral 0 to pi over 2 of 1 minus 2 cosine theta plus cosine squared theta. And let's see, cosine squared is, for sake of integration, is 1 plus cosine 2 theta over 2. So you can split that, 1/2 plus 1/2 cosine 2 theta. So add the 1/2 to the 1, you get 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. We got 4 integral 0 to pi over 2 of that. Then we integrate 0 to pi over 2. We get 3/2 theta minus 2 sine theta plus, so you integrate cosine, you'll get sine, but you get to divide by 2, so 1/4 sine of 2 theta. Still multiplied by 4. I've got enough different things in there. I figure I might as well well, I'll keep the 4. I'll keep the 4. So that's, by the way, is 2 pi. 2 pi I gotta add. So then plug in pi over 2. That's 3/2 times pi over 2 is 3 pi over 4. And then, let's see, plug in pi over 2 to sine, you get 1, so minus 2. Plug in pi over 2 to sine 2 theta, that's sine of pi, which is 0, so plus 0. Plug in 0, you're just going to get 0. So multiply the 4 through, you get 2 pi plus 3 pi minus 8, so you get 5 pi minus 8. And just looking at, where's the last slide, I think. If we want to do an area between two radii, it's just the same as if you're doing it with a rectangular integral. So say you got one radius down here, one out here, you know, you want to do, say, between those two angles, well, you have to do this radius minus this radius. You basically have to do the subtraction of the areas, just like normal. So let's do one where we have to find the area between. So here's exercise 15. So we want to be inside the circle, negative 2 cosine theta, and outside the circle, r equal 1. So let's take a look. Plot r equal 1 and r equal negative 2. I'll just delete until I get there. Negative 2 cosine theta. Take a look. There's r equal 1. We want to be inside this and outside this. So we want to be from here to here. Well, you can tell where they intersect is, well, I guess we can set them equal and see. When 1 equals negative 2 cosine theta. So cosine theta equals negative 1/2. That's at basically these two quadrants. So it'd be 2 pi over 3 and 4 pi over 3. And I could do the integration from there to there, but because I'm pretty sure it's on the same point with both ones. Let's verify that. I think so. 2 pi over 3. Right there. Right there. Okay. But since it's symmetric vertically, again, you only really have to find one of them, and it's from there to there, so that's from 2 pi over 3 to pi, and then we can just double it. So we want to do 2 pi over 3 to pi, doubled. The outer function then, the outer radii, is this one, the negative 2 cosine theta. So remember, don't forget 1/2 squared, so 1/2 negative 2 cosine theta squared. And then we're subtracting 1/2 times, well, I mean, it's a very simple thing. It's 1/2 times 1 squared. But I mean, it's really just this half of the circle. Because since, or quarter of the circle, I guess, since we're just going there. But I suppose we can put that in just to be safe. Yeah, this formula is just r equal 1. So from there to there. I guess it's not even really a quarter of a circle. So it's probably simplest just to do that. You can pull out the 1/2 and cancel with the 2. So it's just 2 pi over 3 to pi of 4 cosine squared theta minus 1. And again, we can do our cosine squared theta is 1 plus cosine 2 theta over 2. So that'll reduce with the 4. And I can multiply by 2. So it'll have 2 plus 2 cosine 2 theta minus 1, which is just 2 cosine 2 theta plus 1. Integrated from 2 pi over 3 to pi d theta. Integrate this, you're just going to get sine of 2 theta. Integrate that, you'll get theta to pi. Plug in pi, you will get sine of 2 pi, which is 0, plus pi, minus, let's see, 4 pi over 3. Sine of 4 pi over 3, oh boy. Let's see, that's pi over 3 in this quadrant, so it's going to be a negative number. This will be plus. And sine of pi over 3 is square root of 3 over 2, so it's square root of 3 over 2. And then minus 2 pi over 3. So this is going to be pi over 3 plus square root of 3 over 2. And here we see the length of a polar curve is given by this. This is just the formula for arc length we did back in section 11.2 when we talked about calculus with parametric equations, parametric curves. We noted there that our length was integral alpha to beta of basically our square root of dy dt squared plus dx dt squared dt. Well, in this case our parameter is theta, so this becomes alpha to beta of dx d theta squared plus dy d theta squared. And if we remember, we actually know what dx d theta and dy d theta are, and these just come from doing our work with x equal, remember, r cosine theta and y equal r sine theta. So dx d theta is, let's see, r prime cosine theta plus or minus r sine theta, because derivative of cosine is negative sine, and then dy d theta is r prime, so dr d theta sine theta plus r cosine theta. So then, squared, of course, will become dr d theta cosine theta minus sine theta. I'll put it here, but I think I'm going to do it off on the side. So dr d theta plus r cosine theta. Oh, I forgot my r there. Cosine theta. Oop. Squared. Square rooted. So you do the work here. That first one becomes dr d theta squared cosine squared plus 2 sine theta cosine theta dr d theta, and then plus sine squared squared theta r squared, and don't forget the r squared. Okay, then this one becomes dr d theta squared. Oh, and that should be minus in the middle. Minus, because that is a minus right there. Dr d theta squared plus 2. Oh, I forgot the rest of it. That was sine theta, wasn't it? Yep, sine theta. Sine squared theta plus 2 sine cosine sine theta cosine theta dr d theta, and then plus r squared cosine squared theta. Alright, so collecting some terms here. You can combine these two, sine squared plus cosine squared, factor out the dr d theta squared. Sine squared plus cosine squared is 1, so that's just dr d theta squared. Similarly with this one, r squared times sine squared plus cosine squared is just r squared. And then the middle term just goes away, because they're the same term with opposite signs. So we now have this. That's our integral. Alpha to beta of r squared plus dr d theta squared times d theta. I did forget to draw in my d theta while I was doing my work, but it's up there. You can generalize because I had dt inside. This becomes dt out as well. If I replace t with theta, it should go out here as well. Now let's look at an exercise. Find the length of the cardioid, r equal 1 plus cosine of theta. So if we look at that, plus cosine of theta. Clear this. Look at the graph. This, by the way, is exercise 23. Alright, so we want to go basically from here to here. We could, again, find half of it and double it. I think I might do that. Looks like from 0 to pi would get a full half of it. If we look at trace, there's 0. We go all the way over to pi. Yeah, we get right there. So let's just do that. 0 to pi times 2. And we're looking at the square root of r squared plus dr d theta squared. D theta. Alright, so r squared would just be 1 plus cosine theta squared. Dr d theta would be negative sine theta squared. So that's 1 plus 2 cosine theta plus cosine squared theta plus sine squared. Sine squared plus cosine squared is 1. 1 plus 1 is 2. 2 plus 2 cosine theta. Square root it. 0 to pi. 2. And if we look at that, I can pull out the square root of 2, I guess. 2 square root of 2. 0 to pi. Square root of 1 plus cosine theta. I think what I'll do with this is I will do the trick of rationalizing the numerator by doing this. I will do 1 minus cosine theta. 1 minus cosine theta. Because then I'll get 1 minus cosine squared, which is sine squared, underneath the root on the top. So then I'll just get sine theta. So we'll get 2 square root of 2, integral 0 to pi of sine theta over square root 1 minus cosine theta. And then we ought to just be able to integrate by substitution. U equal 1 minus cosine theta du. Oh, that's convenient. That's just sine theta d theta. So this becomes integral. Might as well change my limits over. Cosine of 0 is 1, so 1 minus 1 is 0. Cosine of pi is negative 1, so 1 minus negative 1 is 2. Let's see, 2 square root of 2, I forgot that part. And then it's 1 over over square root u, so u to the negative 1/2 du. So 2 square root u. Increase by 1/2. Increase by 1. You get positive 1/2. Divide by it, you get another 2. So this is times 2 again. U to the 1/2. So that's 4 root 2 times the square root of 2 minus 0. So 4 square root of 2 times 2 is actually going to be 8. And there's our answer. That'll be it for this video. Thanks for watching. What we have left to still talk about in a class would be talking about the conic sections, which honestly a lot of times you first encounter in college algebra. But we'll get to those when we get to those. That's all of our discussion of polar coordinates, so see you later.